And welcome to these great events. We are very delighted, guys, today to talk to you about functional approach to reactive microservices. These presentations will go through a framework we built to tackle these problematics. The framework has been built in Scala, but as you know, those concepts, they go beyond a specific language programming, so we will touch all these principles in the presentation. If you want to find more about the framework, it's an open source framework. You can go to GitHub, reactive-platform, and you can find the code there. And I more than welcome you to be a contributor of this project. So before we get to the hardcore of this presentation, let me spend a couple of words to tell you who we are. Our company is called Edison Global. We are a brand new company about to launch our platform to the world. We're going to be a betting and gaming company. And by being a betting and gaming company, you have lots of challenges. We every day have to deal with fault tolerance, be available 24/7, and we have huge loads of people. You can imagine now the final of Champions League, how many people will be interested to follow that match and eventually place a bet. If you want to find more about us, we have a stand here in the area too, and our engineers build an applications, and we are running a competition called the Move On Up competitions. You're more than welcome to join us, come there, play the game, and if you win, you can bring home take home a brand new iPad 12-inch. And of course, we want you to see to come there and talk to us and learn a little bit about our technology. So, who am I? My name is Patrick Di Loreto. Oops, that's Jose. That's not me.
Hey guys.
I'm the CTO of Edison Globals, and I have spent the majority of my engineering life building distributed system, highly concurrent system, and this includes also big data platform, because concurrency and parallelism is quite important there.
Cool. Hi guys. My name is José Luis Escanciano. I'm Chief Architect at Edison Global, and I consider myself as quite passionate about distributed systems. I've been spending the last 5 years working on different areas, all connected to distributed system, from development into the architecture, design, and principles. Just so without anything else, let's jump into the main topic. So, as you were saying initially in our title, we have a lot of fancy words. So we have reactive, we have microservice architecture, we have functional. So let's try to shape everything all together. So my goal in this first part of the presentation is to drive you through which are the principles and foundations that we are envisioning for our platform. So the first one is the reactive principle. So most likely a lot of people has already heard about this. So can you please raise your hands, whoever has heard about this before? Okay, quite a lot. So this is a good educated audience. So nice. So for those that you didn't raise your hand, so let me try to spend some words on what all of this is about. So reactive principle is about delivering responsiveness to our customers. And responsiveness is nothing else than be able to respond in a timely manner. What does it mean? So nowadays, we have like a very different use cases than we had before. So now it can be the case that we all together go with our friends, we go to a restaurant, and then we have a nice meal. And then by the time we need to go and pay the bill, I actually give my debit card to the waiter and actually realize that, God, I don't have enough money there. So I just grab my mobile application, I go to my bank, I top up quite fast onto the debit card because I don't want to be a shame in front of all my people. So these kind of things, well, obviously this is a quite extreme use case, but there are many others that are quite illustrative as well. So these kind of things are the kind of use cases that we have nowadays. So we cannot afford to deliver responses to our customers in not a timely manner. But responsiveness has to be delivered in two different forms, on two different ways, which are from one side, sorry, this thing is not working properly. Yeah. So from one side, we need to be prepared to respond under different kind of loads. Why is that? Is that because, well, long time ago, when we were designing our systems, our target audience was pretty small. Nowadays, we go into a global environment. We are targeting Spain, we're targeting UK, we're targeting Brazil, we're targeting the Hong Kong, and all of the time our system needs to be ready for all those customers that are going to consume our service. So just think, for example, into a global agent in the market. So is, for example, Amazon, that is all the time up and running. And when they have offers like the Black Friday, everybody's just waiting for that midnight when the when the clock ticks, to get into the website and start to order massively. So they are going to hammer their services, and their services needs to be prepared to scale out accordingly to support that amount of load. Moreover, the fact that all those customers goes all together increases a little bit the chances that a failure happens. And we need to embrace failure because it's something that we cannot get away from. So we need to be responsive under failures as well. So we cannot afford to give to the customer the sense that something is going on, going wrong in our systems. So we need to also design our systems to be able to isolate the failure as much as possible. And finally, as an enabler for all of this, we have a message-driven approach. Good. So up to this moment, we have just ticked the first word on our title. So next thing we're going to try to tick is microservices architecture. So as a lot of you probably have already worked on these big angry guys, these big monoliths. Long time ago, the way that we used to design our system was just to put more and more responsibilities here and there into a system that grow and grow and grow, and it came to a point that it was just not maintainable. So we want to get away from that, and we're going to give an answer to how we design our system. So we go now into microservices-based architecture. What does it mean? So it means that now, instead of having all the responsibility in one big guy that has to handle everything, we are splitting that into different microservices that are going to handle that. That's actually a good opportunity to meet the reactive principles that we were talking about before. Why? Because now, because we have different microservices, it's much easier for us to design and isolate different regions of failure. So the fact that one of those little microservices fail shouldn't afflict the whole system. We need to be able to respond under those situations. And also, because those guys are going to have different responsibilities, we know that many of them are going to have really different amounts of load to deal with. So for example, if you think of registering customers, it's an operation that doesn't happen too quite often. But on the other side, if we are talking about placing bets, it's something that happens every second a lot of times. So the way of designing this with microservice-based architecture allows us to scale those services independently. Good. So now we need to talk about our necessary evil. Can you figure out which is our necessary evil? Which is the source of the main of our complexities all the time? Is the business. We need to be able to design our systems to respond to our business needs. And the same as before that we were seeing with the monoliths and the microservices, business wants just to put more and more and more and more requirements, and we cannot just afford to grow that without any control. So what do? We apply domain-driven design, which is pretty much a divide and conquer. So instead of tackling one whole domain, what we're going to do is just split that into different little subdomains and tackle them separately. That actually brings to an idea of how is best to split that whole domain into different subdomains. Most of the time, that's going to reflect how your company works, which actually is reflected on the Conway's laws. But at the same time, most of you probably have been working on different methodologies like Waterfall or Agile. This is a good opportunity to match into an Agile team because our business analysts and product owners are going to be the experts on our domain, and then our engineer team is the one that's going to translate that model into microservices, for example.
It's not responsive.
Yeah, it's not responsive enough. This is not well designed. So what is DDD also about? So you can go into many presentations what DDD is about, but at the end of the day, DDD is about modeling, right? So it's not just splitting your whole domain into different subdomains. It's also about how you model those domains. That's the thing. And it gives you like the tools on the box in order to build your domain model, actually your best model or your top domain model, which probably looks something like that. Well, not quite like that.
He doesn't want to change it.
But just to spend a couple of words about a domain model. Obviously, the domain, we talk about that, is all your business needs split into smaller subdomains, and then we have our model, which is nothing else than a set of instructions and behaviors on top of that model. And there is here one thing that is quite interesting, and I will talk about that in a minute, which is the ubiquitous language. Sorry for the pronunciation of that ugly word. Let me put an example. So back all those days, if we have, for example, we are modeling a hotel business where we have registrations, we have bookings, we have finance, we have everything. If we are trying to model everything together, it's going to be quite difficult to run away from a monolith approach. So what we need to do is to split our domain into different subdomains and then tackle them separately. What does it mean? So, for example, in the registration side of things, obviously our guests are going to be formed of many different fields, like, for example, first name, surname, date of birth, and who else know. But from the point of view of the bookings, that might not be quite interesting. The interesting thing about a guest is going to be just its ID, pretty much, and then obviously which room you're booking, and so on and so forth. What means is that same things that are in the reality are going to be modeled in different way in the different subdomains. But the important thing is that we define, along our domain model, we define a ubiquitous language, which means everybody inside that subdomain will speak about the same things in the same way. And now, how can we actually model our subdomain? So there are different things in our toolbox to do that. So the first thing, a simple thing, is a value object. So a value object is nothing else like, is an element that is not intended to be changed over time, which means every time you change it, it's a new value object, which, for example, can be an address. You change the address, it's yet a new address, nothing else, nothing fancy. The next element we have in the toolbox is the entity, which the main difference with the value object is the fact that it's intended to change over time. So, for example, a value object can be one of our customers, which, by the way, is formed by different value objects, like address or name or whatsoever. Obviously, those things does not appear in isolation, so that's why we call about aggregate, which is an aggregation of those things that, by the way, are going to be like the entry points of our APIs and our unit on consistency in the model. And finally, because we need to also model the behaviors, amongst them all, we have the services, which are pretty much what describe the behaviors. So now I think we have more or less a good idea of how we can get to model it, but now is the moment to materialize it into something. So that something actually is abundant context. So abundant context is nothing else than the kind of the materialization of that domain model, which is intended to be self-contained and potentially self-deployable, but obviously that doesn't mean that they appear in isolation. Actually, quite often they communicate between each other, and there are some tips there that will actually help you when you are defining your bounded context. It's true that they interact with each other, but actually because of the inherent properties, we need to keep that to the minimum. So now we have kind of a lot of things that we have talked about. So let's see how all of this materialize in a reference architecture. So from one side, we were speaking about our bounded context, and all of those microservices are going to be the representation of the materialization of our domain model. And as we said, we need to follow the reactive principles, right? And one of the main things, the enabler for the reactive principles is to be message-based. So for that reason, we put in place a message bus to be able to communicate through it. Then those guys are going to start exchanging messages, but because we want to build a protocol to know how those things are communicating all together, we are going to define those things like command events, request responses that Patrick is going to introduce short on. And the final piece is, obviously, up to this point, we have our system, but it's not communicating to the outside world. So we need to put in place something that allows us to communicate to the outside world and actually to third-party systems. And this, essentially, is to cover now how we are going to implement this, in which manner we're going to implement this. I think is the second part of this presentation, which Patrick is going to guide you through.
Fantastic. Thank you, Jose. So one element is missing so far. We talk about reactive, we talk about microservice. The question is, where is functional in all this, yeah? So we don't have to forget that we are building highly concurrent systems. And probably the majority of people here went through the pain to write multi-threaded applications. And we know that when you use variable and object-oriented programming, most of the time you end up dealing with the problems of deadlocks. You use primitive like semaphore and locks. Now, we want to find a paradigm that allows us to reason about the problem of concurrency from a different approach to make things easier. And that's where people started to go back and say, oh, wow, how cool is lambda calculus? Actually, we can apply in today's applications to deal with the complexity of concurrency. So functional programming is nothing else than approach these problems from a pure mathematical point of view. We love functions which are pure, and pure means deterministics. So upon the same inputs, you produce the same output. And if you have a concurrent system, this is a very powerful tool because you can describe the behavior of your system in an effective way. So what we're going to do in this second part of the presentations, Jose told us about lots of good stuff and architectural principles that we put in the framework. And that was a top-down approach. In this second part of the presentation, I want to take you through the journey from the different angle. We will go bottom-up. We will be building the key components using some Scala code of our framework, and hopefully we will be able to fulfill all the principles that Jose told you just a second ago. So what is at the very core of our system? I think the best way to start this is talking about domain-driven design. We need to implement systems, and behaviors are the key elements on a system. And behaviors are performed by services, as we saw in domain-driven design before, which is the best way we have to describe a service. A service is nothing else than a relationship with the elements of our domain model and establish a relationship of causality. Given certain constraint, given certain input in your domain, you produce certain effect, certain causes. And functions are perfect to describe these elements. So a service, in its mathematical form, is a function generic in an input in and generic in an input out. But because we are human and we love to add semantic to the behavior, we're going to label with a name. Okay, some of you can argue, fantastic. Functional programming, Patrick, very cool, but which kind of problem are you solving with these functions? You know, if you have pure functions, you cannot very far. The complexity comes in your systems where the status is living, where data are. How do we manipulate data? Those are the primary cause of side effects and concurrency coordination. So what we're trying to do here is try to have a different approach. We know how to do with object-oriented programming, of course, encapsulation, hide the status. I'm going to give you methods to manipulate the status. Oh, but methods are not deterministic, so I go back to the old way to do things, locks and semaphore, and I don't want to go that way. So we need to do a little trick, and it's the responsibility of our framework to provide to the developer with a tool that can handle this complexity. We want the developer to describe side effect on data using pure function. So how are we going to do that? With my responsive clicker. Unresponsive.
I'm going to implement responsive.
Please, Jose, be my clicker.
There you are.
Another time.
Fault tolerance in place.
Fault tolerance in place. So that's our friend, service. Service, we said generic in and in out is a pure function from in and to out. Now we need to put the status. So we said that this is describing causality. And now we have the status. The status is changing as well. I'm going to try my clicker now. Fantastic. So the little trick I would like to do here is nothing stops me to say that a service in its input type is a tuple. And this tuple is generic on S, which represents my status, has an input which represents an action I want to perform on it, and the outcome will be the final status and the output. I took the time out of this equation. I'm describing causality. Certain input on an initial state going to produce an output with a final state. This is deterministics. We need to make sure that there are no other agents interacting here. So that's the first step to say, look, Stateful service generic in as input and output is nothing more than an alias of my friend's service where the in is as input and the out is as output. Okay, all with me? Any question at this stage? We're going to go to the interesting part now. Okay, so let's go back to our function. And let's look at the function. Okay, I apply those substitution, Patrick, and I have SI and SO. We know why. We already spoke about this 1 second ago. Now we will do some massage, manipulation to this function. And you know, there is no reason in the world that status and input should be provided at the same time in an eager way. I don't need to provide this input to the function simultaneously. Anybody knows the way to make this lazy? What is called? How many of you knows currying? Currying is coming at our help. This slide is saying, look, there is no reason I have to give the two inputs at the same time. I'm going to first give you the action I, which is going to return you a new function. Remember, functions are right associative, so we can look at this. I give you an input, and then I'm going to give you back, after you give me the input I, I'm going to give you a functions that, given an initial status, give you the final status and the manifestation of side effect. So we are separating concern. This second function is the causality and manipulation on the status. This is specifying the input. And of course, both of these elements are available in this implementation because we all know what closure is. So let me put some formalism. And you know, the one that loves functional programming and monads might recognize that this kind of function is a state monad. And there are very good properties to be a monad. But don't worry, if you are not into functional programming and monad these stuffs, bear with me, this is just a type representation of this function. Is how we manipulate status, and how we handle the side effect of manipulate status. So if you're not comfortable with this, please consider state of SO just an alias type for the function we described before. And we can come with our definition of stateful, generic in SIO, and now is a new function that given an I produce a state of S of O, which is nothing more than the same function we have seen before. It's a different way to shape it with more precise types. Okay, we are missing one element. We're talking about responding in a timely manner, the way that this clicker is not working. But our customers are expecting we respond in a timely manner. And we need to make sure that our services are not blocking and waiting the result of functions to go ahead. We need to make them asynchronous. The developers can describe all the behavior in a pure asynchronous way. So we need to transform our service into what we call a reactive service, where our generic in I/O, the input type remain the same, but the output now is dropped into a future. This future is representing the behavior to respond in an asynchronous way. So now our new function of service is a function that goes from I to a future of O. And if we want to transform this in a reactive stateful service, well, we just need to remember that O was our type state of S of E. And applying this substitution, da-dan, we get reactive stateful service, generic in SE, I, and E, and we get a stateful service, generic in I, and produce a future of state of S of E. And below there is the functions that represent the reactive service. Very good. We have a solid definition of service which are asynchronous. They manipulate status and allows the developers to describe this in a deterministic way. And the framework will care about the concurrency and the distribution of all these. What can I do with these functions? We know these functions are manipulating status. Now we're going to give a meaning to this function. And this is where Jose before was talking about command, request, events. We need to associate a semantic. And the way we do it, we recognize that there are several semantics. There is a semantic of a stateful service that if you have a status and I provide you a command, you modify the status and you emit an event as manifestation of these status changes. So if you think about the booking application that Jose was talking before, I go into a website, I register my account, the system going to store the new account, the global system status has changing and emit an event, customer registered. But the only way to manipulate the status is not only through commands. Systems are reactive. I might have an email system in my applications that wants to send a welcome email to every single customer that just registered. So we have a second type of functions that react to events. This function is observing all the customers that has been registered in the system and decide to issue and send an email to them. So this is the reactive aspect. But we cannot forget that there is a third element which is equally important, Sometimes we make requests to the system not to generate side effects, but to extract information, what we can call the read side. So we issue requests on a specific status to get a response from a system. And this is maybe when you load your profile page and the website has to issue a request like get account informations. It's not generating side effects, but it's accepting a request, it's elaborating on the status, and it's producing a response. And this is not brand new science. We all know that this is coming from somewhere. And this somewhere is called CQRS, which is Common Query Responsibility and Segregation. Now, it's not part of this presentation go deeply in what CQRS means. But the takeover I want to have here is that when you build this system, you are conscious that there are two subdomains, submodel on your system. There is one part of your system, some behaviors that are responsible to manipulate status. And in CQRS, they call this the write side. And then there is a different part of it that is the representation of your information that serves the read side, the request. So CQRS is somehow saying, divide these two elements, because actually you can scale them differently, and we can identify these two behaviors. You know, the command we have seen before and the event reaction we have seen before, they belong to the write side. Request response is the read side. In CQRS, we formalize these, and we call the write side processors, and we call the read side views. So the processors actually are the microservices responsible to manipulate the status. The view are the microservices to serve the request. Now, let's give a more formal, and let's use some code to describe these components. So processor is a trait, a component, an interface for a microservice. It's generic on the type S, which we know is the status. But please allow me now to enrich our vocabulary. The status is nothing more than what Jose was calling the root aggregate in domain-driven design. If we don't want to go to the root of the domain-driven design, then stay with that, is the status. So what the processor is doing to the root aggregate is manipulating the value. So the processor is nothing else than the set of definitions of function that, given the status S, which is matching the root aggregate of the processor, a command can produce the final status and emit an event. But we know this signature. We know very well that this, guys, is the stateful S command event, which in the last slide we call these types. Now, we know that the write side has also to react to other events. So no surprise here, seeing that we also have these other kind of functions, which again is a stateful service, generic and S event and event, which correspond to our type set of events. Let's move on the read side. We're going to play the same game here. The read side is responsible to represent your information in a way that is effective to perform requests and get the right response. So it's generic on the status S, because the read side has a status. It's the status that going to use to query and extract the information for you. And again, it's the root aggregate. And no surprise, the kind of function it's serving, getting an initial status and a request produces a response. We don't need the output status here. Read side, no side effects should be performed here. Again, with some cheating here, manipulations, we can say this is a stateful service of S request response. Some of you might already have spotted, Patrick, you're cheating. Your function is returning the status at the output. That's true, but I'm going to ignore it. So they're going to work. And this is a set of asks. But now there is another element. My status, even for the read part, need to be updated. Otherwise, I serve always all the information. My view needs to be reactive, need to be able to update itself. So no surprise, guys, if here I tell you, I need this kind of functions, reactors, that if my read side subscribes to some events which is interested, it needs to update its internal status and emit an event to create this nice butterfly effect in your system. So we know these types very well, and reduces into a stateful service of S event, and ultimately AVT of S. Okay, let's put everything together. I think we are getting where Jose was at the end of his slides. Now, take your systems, take this set, your microservices, which are the set of processors and a set of views. These processor views, they were generic on the type S, but the type S is the root aggregate. So the set of root aggregate is your domain. And the processors and views are your microservices. We put them together, we give a name, and this is the bounded context that we are building. Now, some word about the framework. So what we have done so far. we have provided a language for the developer to describe their system. I want to create an account system, a system that can manage accounts, and this is my bounded context. And I'm going to put processor that can elaborate the registration process and other views that can provide you the information of the accounts. And all these microservices collaborating together is going to deliver the whole bounded context system. So the developer uses a declarative way to describe the behavior and the data he wants to use. The framework is responsible to distribute these services independently, is capable to be fault tolerant, because if your service is running in one node, going to be then running into another node preserving the status, and you can scale each of them independently. How do we do that magic? Well, we don't do that magic. We use the work that other people did. In particular, Jonas Bonner, that today going to be speaking here, and the creator of the Akka framework. We see an actor model an effective way to describe all these systems, and we leverage different modules of the Akka model. Akka is a good model to build concurrent systems. Akka clustering extensions is the way you can distribute these elements. Akka persistent is how you can manage distributed system status and be fault tolerant. But enough of words, and let's look at some code. Over to Jose.
Cool. I'm conscious of the time, but it's going to be quite fun to see a little bit of code of this framework. So you will see how easy it's going to be for us, thanks to this, to model our domains and implement them.
If you want
so
you can use the components.
Yeah. Is it big enough for everybody to see? Right, so what do we have here? So we have here like the last thing that Patrick was talking about. So we have our definition of a bounded context here, which we are going to tag with a name, actually an ID, and we are going to version it because we know that those things evolve over time. As Patrick was saying, a bounded context is form of many different components with nothing else than a set of processors and views. Then bear with me a second, just those things what are about is to abstract away how you can get to deploy these services. So this platform install bounded context is the one that actually is going to materialize this bounded context into different nodes, and also, for example, because we are using as our message box, we are using Kafka, sorry, that part is responsible for creating all the different topics that are going to be needed. So let's dig down into the wallet processor implementation. So you're going to see now that we are defining how a processor looks like. And this is essentially how our stake will look like, which in this particular example, we are modeling a wallet system. So for that reason, we obviously have a wallet. And for the simplicity of the example, we model it with just an ID. For example, can be the wallet of a given customer, the amount, and whether that wallet is active or not. OK, we follow with a definition of the processor. And obviously, we name everything in our domain. So we give it the name of wallet processor with version. And then we have here what is called the descriptor. So the descriptor in this part is what Patrick was referring to in the last part of the speech, which is how we actually deploy this in a way that we can distribute the load. So you will see here that we have something called sardine descriptor, and this matches to the Akka sardine region. So that will allow us to distribute the load of this aggregate across different nodes. And then after this, obviously this is the initial state of our model right here. And finally, all the different stateful services that we are implementing. So we have here a few of them, which are create wallet command for the creation of the wallet, debit wallet command, which is for debiting money from a given wallet, and then crediting money to a given wallet. And finally, just to illustrate a little bit how the status of a given wallet is in a given moment in time, we have one query here, which is a get balance request. So let's dig a little bit into what this is about. Do you see it correctly? So as Patrick was saying before, this is a command, actually, a stateful service that gets a command. The reason why there is a context CTX prefix is because we want to ease to you guys when you use this and you implement it, the fact that you might need to access to different facilities, like, for example, any repository or any discovery service or stuff like that. So then the definition of our create wallet command is actually a stateful service. This is our state, and this is the command that we accept for this stateful service. And what you see in here is just the implementation that you need to do in order to implement this service. And finally, this is how we are going to name this stateful service.
So let me jump in here, guys, and make sure that you can recognize from the slide. If you see the create command, you can see that the input tuple is the initial status and the command. And we return another tuple, which is the final status and the event. This is our friend stateful service we have seen before. Generic in command and event.
And then if you see the code of these other stateful services that we have over here, one can argue whether this is too functional or not too functional, throw an exception, is it a good thing or not? So bear with us. The thing is, our framework is handling it behind the scenes, and actually this is going to be transformed into an either of something that happens or an error happening. The last thing that I would like to show you is how we are modeling a request response stateful service, which is nothing else than is pretty much like the other one, but in this case what we have is a request, and we have on the left hand side, the Patrick said, is the initial state, and then which is the request that we are actually serving, and that function needs to return an object of type a response, which in our case is a get balance response, which essentially gets which is the wallet ID from the request, and then inspect the status to be able to confirm the response. Do we have time to demo?
No, we have been told that we have less than 10 minutes left. We are very keen to show you how all these things is running in a runtime, and we have a Docker composed file that can create a distributed system, and we will be playing destroying nodes and show how everything is resilient. But it doesn't mean we don't have time now to show right now in this presentation, but it doesn't mean we don't want to show you. So you are more than welcome to come to our stand, and we will show this framework in action. But now we need to leave these times for anybody who has questions and wants to know a little bit more about our presentation. So up to you guys.
Thank you.